back to another episode of Car Chats with Herbie. Now, I wanted to discuss about how engines are sealed and the advancements in engine sealing with the change of technologies. And now we have what's called liners within car engines, heavily utilised within aluminium engines generally, as the aluminium against aluminium, there's high friction rate between the two materials, and they can prematurely wear. High friction creates heat and things like that, and resistance, and so they usually have a steel liner, which is a hard wearing liner, which is like an insert within the cylinder bore itself, and it basically means that once that hard wearing surface wears out for the piston to reciprocate up and down, it means that you potentially don't need to replace the whole cylinder block itself, which is expensive, and basically you talk about a new engine or an engine rebuild, and it means you can have a more mild rebuild. You can replace the liners and things like that. Now, in 1967, a company called Mahle, M-A-H-L-E or E-L, a German company, now invented and patented a hard coating which composed of nickel first, silicon, and then a carbide. And this coating meant that we could get rid of these liners. We could increase the capacity of engines. We could increase diameter of the bore. We could have alloy on alloy, because we had this very thin micromillimeter coating around the engines, the cylinder bore itself. And this was the reason it first came around is because they were trying to find a material which was hard enough for the rotary engines, for the apex seals, as apex seals run across in a rotary engine, run across the bore itself. There is vibrational friction as it tries to resist but move around, and that can shatter and break, and they later went on Mazda and things to create split apex seals and things, so it could cope with that vibrational torsion within the engine. Now, it was then adopted by Porsche early on in their 917 race car in 1970, proved to huge success. Later in the 911s, because all these 911 engines were flat or box orientation, and they were aluminium, and this meant that you could have an aluminium cylinder block, an aluminium piston, and you could turn down there, and you could use the same material throughout the engine block, increasing the lightness of the block and resulting in less inertia, better fuel economy, because there's less reciprocal mass, there's less force needed to overcome the change in rotation of the engine. So going from inertia, a constant state, to applying inertia to inertia, that means that it could move up and down, reciprocate up and down the bore easier. Less weight as well, so less reciprocal mass, means it revs higher, revs quicker, spins faster, creating a lighter engine, lighter car, lighter package. And this liner was adopted in the Porsche 911 turbos and things like that. And in an air-cooled engine, if you can get rid of that steel liner or cast iron liner, which is usually composited of like a grey iron with graphite, or modular iron, which is a very common formation of iron. It's cheap, it's strong, and it works well. Now, it also helps if you can get rid of that, as I was saying, you can get rid of that thickness between the aluminium, which is good at dissipating heat and conducting heat. It's got good thermal expanse, got good thermal conductivity, It transfers heat quite well, does aluminium. It cools down quickly and things like that, which is ideal for air-cooled applications like in the Porsches and the VWs. And if you can get rid of that steel bit, it means there is less of that heat retained within the cylinder, meaning that you can have better thermal properties and keep the aluminium engine cool, especially because they were air-cooled at the time. It's like that. Now, NIKASIL was in a lot of 70s, 80s, 90s cars. It's extremely hard wearing. Usually when you require new piston rings or things like that, and as well with aluminium engines, you have to remember you have to have a special alloy piston ring if you're using alloy pistons, alloy cylinder blocks and things like that, and usually alloy componentry, because it doesn't have the compression strength of a steel or a forged steel because of its grain structure and things, and because it's being a slightly softer metal, it means that you have to double up the thickness of the alloy componentry, but it's okay because it weighs around 2 to 3 times lighter than a steel and things like that, so you can sort of get away with it. That's why you find connecting rods are thicker if they're aluminium and things like that, and the crankshafts are usually thicker. But yeah, then it came problematic because in the 90s, max that, there we go, in the 1990s, the fuel additives changed and the fuel quality changed. It actually got worse. They do say that fuel from 70s, 80s and earlier was higher quality fuels generally, but because of emissions and things, times change due to emissions, they had to adapt and change the fuel types, additives and things like that. And as car engines got more advanced, they needed fuels which were more resistant to pre-ignition and things like that, and had lower amounts of particulates in parts per million produced out the exhaust of things. And with the rise of catalysts, you need to get rid of things like lead triethylate and things like that within the fuel. And let's get past this bus, give it a go. Oh, you're wrong. And now that meant that the sulfur, got a bike coming past quite fast actually. Right, I just got a bit distracted there. Sounds quite alright actually, that, to be honest. Nice bike that. Sounds like an inline 4 Honda or something, that. So quite a high pitch. Anyway, I've got distracted there big time. Back to NIKASIL. Now, in the 1990s, fuel changed, as I said, additives and things like that, and this meant the lower grade fuel with the additives and things. It also was a form of cost cutting as well. They can get the energy density out of putting artificial things and taking away less petroleum mass within the fuel, meaning that they can make more money because they're saving the amount of petroleum and oil within the fuel. And then this meant that the sulfur within the fuel reacted with the NIKASIL. And what happens? What do you think happens when the sulfur reacts with the NIKASIL? Yes, it creates an unsealed chamber because it wears down the bore. It wears down the bore. Turbo shifting. It wears down the cylinder bore, and that means that the NIKASIL starts to wear away, and it creates an unsealed chamber, and compression gases can pass, creating huge crankcase pressure and blow by. And this also means that the oil can go past the piston skirt, contaminate with the combustion gases, leading to high amounts of oil burning, fouling the plugs, fouling the compression cycle, things like that, clogging up the catalytic converter, leading to the necessity for engine rebuilds and things alike. Now it changed to what's called ASIL, and now this is a different form of seal compared to NIKASIL, and it first was sort of patented in 1927 by a German engineer. I forgot what his name. It was motor working at the end or something like that. It was actually first implemented on the Chevrolet Vega in the early 1960s, and then it was adopted by BMW in 1996 as a response to this high sulfur content within fuels. Also, sulfur reacts with catalytic converters and can damage the plutonium, palladium, and radium within the catalytic converter. And they changed to this NIKASIL, and it differs from NIKASIL because it contains 73% aluminium and only 17% silicon, and the rest are other composites of metal materials. Now, instead of having like a painted on or electricized on coating, basically they machine the engine block back, so the cylinder bore, until it exposes the silicon and alloy around the bore, and it creates a natural hatching when they machine it out like that. Now, these also have their fair share of issues, like Porsche used it, and the problem when Porsche used it is there was some steel at the bottom of where the cylinder of the cylinders travel within the engine block, and that would create like a galvanization effect, and these metals wouldn't mix, and it would basically damage the hatching within the bore, leading to scoring, and you would have high amounts of oil burning, things like that, and some cylinder chatter as starts to be some play. And yeah, NIKASIL is what's used in most alloy based engines now. Also, alloy engines, they can improve fuel economy, they have good thermal conductivity, they're lightweight, but you do sacrifice longevity, and they don't react well with any overheating, as the metal is very thermally reactive. It's quick to expand, and what you get is called metal bloat, where your cylinder, if it gets far too hot, will start bloating within the bore, and it'll literally friction weld, heat weld itself together, and when you cool it down, it'll stick in the bore, and you'd heat seize the engine, also the bearing races and things like that. And that's another story about the K series. That was a low pressure cast aluminium cylinder block and head, and what it meant is that like a bathtub, they would, instead of pouring the cast in, it would fill up into the cast, which allowed less oxygen to enter, less oxidization into the cast, meaning that the structure of the cast and the molecular buildup of the grain structure and the particles of alloy was tighter and things like that. But it did mean that they had to use a alloy that was quite soft and brittle called TP25, and this meant that it was quite fragile itself and couldn't really take engine knock, pre-ignition scenarios, things like that, and they had issues with the brittleness of the block, especially when they had problems with overheating and you cooled down and it would crack. And also they used wet liners in the K series. First came out in 1988 on the Rover 200 and things like that, late on the Metro and the Rover 100 and things, with the K8 variant, 1.1 litre, 1.3, 1.4, 1.6, and the 1.8, which was a modified 1.6, longer stroke connecting rod, slightly altered cylinder block to accommodate different crankshaft throw and things alike like that, and slightly different passages within the engine block as well. And yeah, the K series used wet liners, so it used, instead of having like a NIKASIL seal around the cylinder bore, it had wet liners, but the disadvantage of that is that if there's any formation of crack and things like that, there's the distance between the oil coolant passages is too close, to the combustion combustion chamber, and where the cylinder lays, and it meant that the wet liner, so the piston's going up here, your lines are here. It does help. The one advantage that it dissipates heat and keeps the cylinder slightly cooler and things like that, which is also good for helping it run a little cooler if it works. And that's the one with Rovers, isn't it? And that can help evade things like pre-ignition knock and those sort of scenarios by having lower cylinder temperatures. High cylinder temperatures are very volatile to pre-ignition, especially with slightly lower RON fuels, which is research octane number. And yeah, so it basically means there's less tolerance between cracking or deformation in the cylinder block casting on the liner, so it would be quick if it did crack for the coolant and oil to mix with the combustion gases, and those to also mix within the coolant ports, leading to the mayonnaise scenario, things like that, and also the smoke out the exhaust through the water burning with combustion mixture, which, as you know, is head gasket failure, and also can eventually hydrolock in serious conditions, where that's probably where you crank the connector over to be thrown at the block because of a hydrolocking scenario. So where the coolant goes into the cylinder and can't be compressed because water can't be compressed. Weakest link connecting rod, as it compresses up, snap. And probably due to poor metallurgy of the casting alloy parts as well. And yeah, the case here was actually the tooling and things was brought by Nanjing Automotive in 2006. That's from in the British. It was designed and built by what they call Powertrain Ltd UK and MG Rover. They sort of designed it in 1988 till 2005, and then Nanjing Automotive in 2006 brought the tooling and rights and patent to build it. They called it the N series, and then it later went on in about 2011 with help from the Ricardo British engineering firm, which also helped with the McLaren engine, by the way. They helped with the McLaren 12C. It was Ricardo Engineering which helped develop that. They're like a performance racing sort of engineering firm, and it became what's known as a Cavacci engine, and actually is proven to be quite reliable. They changed things like the passages for coolant and oil. They also changed the crankcase design and the cylinder head design. As you know, the K series had a bolt which went all the way down. It comes from aircraft, actually. In First World War, it was first sort of seen on light alloy engines to have a long threaded bolt, one modular bolt, which went from the top of the cylinder head down the cylinder block and into the crankcase. But it did mean that torsional rigidity, compression